Now we are going to study one of the most important publication of the semiconductor materials. To control the one of the good things using the semiconductor is you can control the charge carrier density by the technique called doping. Here's the things: donor and acceptor. In our technology, we still frequently use a silicon as a key player in the semiconductor materials, and silicon has the 6 electrons in the second orbital, so 2 electrons in 2s and 4 electrons in 2p. And the silicon itself has less charge carriers. So to control the charge carriers, number of charge carriers, so people find how to increase charge carriers by doping phosphor. So what it happens is phosphor is next to silicon in the periodical table. So 1 extra electron it has. And doping is literally one of the atoms are included in the silicon lattice. So what happens is quite similar to the silicon, but phosphor has an additional electron here. And this electron is kind of like shared by the other atoms. That's why this electron can move around as a free carriers, like free carriers. So it's more like this extra electron is confined in the Coulomb potential of the positive charge centered at phosphor, and it's like electron in the hydrogen atom. So based on this hydrogen atom calculation, we can calculate how much this electron can be stabilized compared with other conduction band electrons. So which can be calculated based on the electron energy level of hydrogen. It can be calculated like E times the 2h bar epsilon square. So which is equal to mgm of 0 and 1 electron volt. Like this. And this epsilon indicates a direct constant of silicon, and so it's a kind of the dielectric property of the surrounding for this electron. So the thing is, these electrons, the doped electrons, extra electrons, has a energy level. The lower the ED, energy of D is, if D is lower than the conduction band, there is some energy levels for this electron state. But since this energy level is quite small, actually comparable to the thermal energy. And thermal energy is, as you already studied, that's at room temperature 26 milli-electron volt. And this doping energy level is about 20 milli-electron volt depending on the doped atoms. So easily, this electron can be excited to the conduction band just by just putting it in the room temperature. So you could increase the charge carrier density. And then similarly, there's another type of doping called the acceptor. So one of the famous doping is boron, which has the smaller, less electron in the 2p orbitals, indicating that that's opposite case. So the opposite charge of electron hole. So in a sense, extra hole is confined in a Coulomb potential, and the calculation is totally same. So this extra hole is stabilized by the center negative charge at the lattice position. And then what happens is the electron in the valence band is easily excited to the acceptor state, and then hole is generated. So in this case, in this acceptor case, the density of a hole can be controlled because this activation EA, acceptor energy level is close to the thermal energy level. So here are the some of the risks for silicon and germanium for donor and acceptor. So you could see there are many variations for silicons and also germanium, but these are, in the case of germanium, the level is a little bit too small to control the charge carrier. But in the case of silicon, it's on the order of several tens of, in this chart, it's like a bit larger, it's 20 to 50 milli electron volt are the typical one. So there are many variations of the controlling the charge carrier density for silicon. Okay, with that, I just like to review the band diagram and how to know the mobility of electron and holes from the band structure, and also how to modify the semiconductor materials by the doping.